The first way we're going to look at for solving this problem is to use the factor theorem. So the factor theorem is that if x minus a is a factor of or divides into f of x, which is a polynomial, then that's the same as saying that f of a is equal to 0. So for this polynomial, if we call it f of x, so that's 2x cubed plus px squared plus qx minus 12, then what the given that x minus 2 and x plus 2 are factors tells us that f of 2 must be 0 and f of minus 2 must also be 0. So if we put the value 2 into f of x, then we get 2 times 2 cubed plus p times 2 squared plus q times 2, take away 12, equals 0. So that gives us 16 plus 4p plus q minus 12 is 0, which gives us 2q plus 2q equals minus 4, and 2p plus q equals minus 2. Now we can put minus 2 into the function, so that gives us 2 times minus 2 cubed plus p times minus 2 squared plus q times minus 2, take away 12 is 0, and this then gives us minus 16 plus 4p minus 2q minus 12 equals 0, which gives us 4p minus 2q equals 28, and 2p minus q equals 14. Now we can then give these little labels, equation 1 and equation 2. If we add them together, then we get 4p equals 12, which tells us that p is equal to 3. And if we then put our answer for p back into equation 1, then that gives us 2 times p, which is 2 times 3, plus the q equals minus 2, so q equals minus 8. Now looking at part B, we know that the polynomial, so 2x cubed plus, we now know it's 3x squared minus 8x minus 12, and we know that this is the same as, and it's, the equivalence, so the equals sign with 3 bars means this is true for all x. So it's not an equation, it's just saying another way of writing something. And we know that that is x minus 2 times x plus 2. And because it's a cubic, there will be a third factor. So we could say, well, that could be called ax plus b. Now, we'll have a look at this in a bit, but what you hopefully will know is that when we have an equivalence with polynomials, then the coefficient of the x cubed, the x squared, and so on has to be the same on both sides of the equivalent sign. And on the right hand side, we can see that the only way we're going to get an x cubed is by multiplying these 3 x terms together, and the only way we're going to get a constant is by timesing the constant values together. So if we were to write this out, we can see that we've got x times ax, so that's going to be ax cubed. At the moment we don't care about the middle terms, but for the constant we're going to have minus 2 times b, which is minus 4b. And now, because of the equivalence and what I said a moment ago, we know that the coefficient of the x cubed, which is 2, must equal the a, and the constant, which is minus 12, must equal minus 4b. So that gives us 2x cubed equals ax cubed, and therefore a equals 2. And we also have minus 12 equals minus 4b, which tells us that b equals 3. And therefore the other factor, and it's important to write it out, is going to be 2x plus 3. Now, in fact, using the comparing coefficients method could be used for the whole question. So what we could do is we could say that 2x cubed plus px squared plus qx minus 12 is the same as x minus 2 times x plus 2 times ax plus b. Now, in fact, the first two terms, you might recognise the difference of two squares, and that gives us x squared minus 4 when we multiply them, and then we have ax plus b. And this is nice and easy to multiply out, because the x cubed term only comes from those two being multiplied. The x squared term only comes from those two being multiplied, and so on. So for the x cubed term we have ax cubed. For x squared we have bx squared. For x we've got the minus 4 times the ax, so that gives us minus 4ax, and for the constant term we have the minus 4 times b, so that's minus 4b. And now we can say, if we look at x cubed, then we have 2 on the left hand side, and that must equal a on the right hand side. For x squared we have p on the left hand side and b on the right hand side. For the x term we have x, so that is q, and that's equal to minus 4a. And then for the constant we have minus 12 equals minus 4b. So we straight away have a is equal to 2, and then using that and using the x term, that tells us that q is equal to minus 4 times 2, which is minus 8. The constant term, when we divide by minus 4, we will get b equals minus 3, plus 3 even. And then for the x squared term, we can see that p is equal to b, so this tells us that p is also equal to 3. So we now have our answers for p and q, and for part b it's nice and easy because we already know what a and b are, and they give us the final term, which we'd written up here. So that tells us that we have 2x. Now there's two nice bits of maths that we've used in this question. We've used the Factor Theorem, which we could see as a special case of the Remainder Theorem, and we've used the fact that if two polynomials are equal to each other, then their coefficients must also be equal. So the coefficient of x cubed, x squared, etc. must be equal. So we're going to have a quick look at them in an abstract way, or if you like, see little proofs of them. So for the remainder theorem, if we think of a polynomial, so we can call that p of x. So that is just any polynomial, and a polynomial is a function which consists of a constant and then an x term, an x squared, an x cubed, up to any power of x you like. So you might have a cubic which has the highest power of x is 3, x cubed. You can have a quartic which would have x to the 4, and so on. So this is any polynomial, and if we divide that by a factor x minus a, then that will give us another polynomial, and there'll be something left over, some sort of remainder. Now, in fact, the remainder hasn't yet been divided by x minus a, and we can see that in an equivalence if we think of just numbers. If we say divide 17 by 3, then that will give us 5 whole, and we'll also have a remainder of 2, but that 2 hasn't yet been divided by 3, so we'd have the answer 5 and 2/3. Okay, so going back to the polynomials now, if we multiply every term by x minus a now, then we'll get p of x equals q of x times x minus a plus r. Now, if we put the value x equals a into this, we will get p of a, and that will be q of a times a minus a plus r, and because a minus a is equal to 0, then the first term on the right hand side disappears and we get p of a equals r, which is the remainder theorem. The remainder theorem says if we divide a polynomial by a factor x minus a, then the remainder will be p of a, or the polynomial with a put into it. And then from that we get that if p of a is 0, that tells us that the remainder is 0, which tells us that x minus a is a factor of or divides into the polynomial. So now we're going to have a look at the fact that if two polynomials are equal to each other, then the coefficients must be equal, which is a technique we use often when solving problems with polynomials. So first of all, we'll just have a little look at playing with polynomials, or well, with cubics on Geogebra. Two cubic equations, the green coloured one and the red coloured one, and we've got sliders for all the coefficients so we can play around them. So I'm just going to change the red one by altering the multiple of x cubed, or the coefficient of x cubed, and then I'm going to see if I can get the green one to match it by playing around with the coefficients there, and see if we can make it match up with different coefficients. Now, if we move this one, that's going to move it up and down, and we can see that if the x value is 0, so on the y-axis, then the polynomial is going to equal this number. So that has to match. So there's no point playing around with that one. But let's see, can we play around with the other ones a little bit? So what happens if we move that one? Oh, well, that's getting it a bit close. A bit closer, that looks better, doesn't it? Still quite a long way away there, but maybe we can just adjust the B one a little bit. Oh, well, that's making the top bit match up, but the bottom's still not looking good. Maybe we could change. Oh, now that's pulling the bottom in a bit, and it's looking like we're getting very close to being the same. But maybe a little bit, but you could try this yourself. In fact, in a moment I'm going to show you that it's impossible, but it feels like maybe we could do it. And this sort of is one of the reasons why we have to prove things in maths, because you might play with this and think, well, I've got it close enough, so I could probably do it if I took long enough over it. But in fact, it's impossible. Okay, so I've said that we're going to prove that the coefficients have to be the same. So we're going to do a sort of quasi-proof by just looking at cubics, and we're going to define p of x as equal to ax cubed plus bx squared plus cx plus d, and we're going to define q of x equal to alpha x cubed plus beta x squared plus gamma x plus delta. And what we're going to do with these is we're going to differentiate them. So just a quick aside about differentiation. I hope you've seen the notation, or if you haven't yet you will do, that we can write dp by dx as equal to p dashed of x. And we can write d2p by dx squared as p double dashed of x. And in fact, we might write d, if we differentiated it lots of times, so n times, we might refer to that as pn of x. This notation makes it nice and easy to say what the first derivative of a particular value is. So, for example, for p dashed of x, we might say p dashed of 2. What that means is what the value of dp by dx is when x is equal to 2. There is in fact a notation for doing that with derivatives themselves, and we could write that as dp by dx when x is equal to 2. So there's always varieties in notation, and notation is extremely important in maths for getting complicated ideas written down in a relatively easy to read way. Anyway, back to the proof. So, if we look at p of x and then we differentiate it, so p dashed of x will be 3a x squared plus 2bx plus c, and p double dash, or the second derivative, will be 6ax plus 2b, and the third derivative would be 6a. Now for q, we'd have q dashed of x is 3 alpha x squared plus 2 beta x plus gamma. Q double dashed, second derivative, will be 6 alpha x plus 2 beta, and then the third derivative would be 6 alpha. Now, if these functions are going to be the same, then we could say that p of x would be equal to q of x. But that would also mean that p dashed of x would have to be equal to q dashed of x, and so on. And then if we look at the cases when x equals 0, we have p dashed of 0 is c, and p double dashed of 0 is 2b, and p triple dash of 0 is 6a, and actually p of 0 itself, which I should have squeezed in there, but I'll pop it in there, so p of 0 would be d. And if we do the same for q, that would tell us that q of 0 would be equal to delta, and q dashed of 0 would be equal to gamma, and q double dashed of 0 would be equal to 2 beta, and q triple dashed of 0 would be equal to 6 alpha. And from these we can see that D must be equal to delta, and C must be equal to gamma, and B must be equal to beta, and A must be equal to alpha. And so if the polynomials are equal to each other, then their coefficients must also be equal to each other. And the point of looking at the proofs is it's really important to understand that everything in maths has to be proven. You learn a lot of very useful mathematical techniques, but sometimes it's difficult to either show the proofs or fit them in, and so it's a good thing to see some proofs from time to time.